Hey, hello students. So today's class will continue with the uh, types of stresses being acted. Last class I think I gave a very small introduction on what were the types of stresses being added with examples. So these are the typical types of stresses we'll be playing around with in the whole course, except the second unit of course. The second unit deals with dynamic or fluctuating kinds of loads. So in this first unit we'll talk more about static loads. Um, so these static loads, what you see is mainly these kinds of tests. Suppose you have performed this tensile test in a lab, right? The material testing lab, I believe. So in these tests, why do these tests are performed, or for what reason you perform these tests, are just to know uh, the modulus, the elastic strengths of, let's say, strength, Young's modulus, shear modulus, also all these modulus of elasticity. Or you can see these are some of the properties: fatigue, strength, resilience, toughness. These are all the material properties. So these material properties will be easily determined by performing such simple tests. So if you perform this test, you'll get a graph, right? You remember the tensile testing graph which you did in the previous class. So you go like it is x versus y. So it will be somewhat like this, right? So stress, which is in term nothing but a load, whereas the x-axis contains strain. This was nothing but the displacement. So this was nothing but the displacement. And for the same specimen, if it was, let's say, mild steel, you did the tension test for this components. So the mild steel is a ductile material. So you get a graph like this, correct? So somewhat like this. So yesterday's class, I told you this is a point where you get your yield stress. So if you plot it in the backwards, and this is the point where you get your ultimate stress, right? So sigma ultimate. So that's where you get your ultimate stress, and this is where you get your yield stress. This is for a ductile material. So this is how it is performed for different materials. So this example for was a ductile material as a mild steel. So you would encounter different graphs such as this when encounter different materials and stuff. So up to proportional limit, whatever you get under this area will be represented by the resilience part, and after that the plastic limit toughness part. So this is how the material properties are determined. This is by performing simple tests such as the tensile tests, you come to know about the properties on how they are found. Right? So yeah, whatever I was drawing is right here. So this is nothing but the sigma. Okay, so Bandari, if you see this is represented as sigma u. Okay, both are one and the same. This is in Bandari. I know VV Bandari, the textbook which is stated for this subject. Similarly, this will be sigma y, such as sy is also sigma. That's how it is there. So this 0.002 or nothing but the 2%. Okay, which is so whenever you strain a material, right? So it won't come back along the origin. Once you cross the plastic limit, so let's assume that there is a plastic limit here. Once you cross this plastic limit, no, it won't come back in the same direction. So it will come back in this direction. Okay. So which means some amount of strain is permanently set. So this amount of strain is permanently set into the material. So that's the meaning of this 0.02% or whatever the length is of the material. So that will be permanently set in the material. That's what it means. So ductility, another property of a material. Once you extend it beyond the plastic limit, it permanently sets. Okay, it does not regain its original shape. You can also call that as plasticity. And brittleness is the absence, is the exact opposite of this. So both of these things, your ductility and brittleness, no, they're opposites. So brittleness is the absence of any deformation. So you will have no deformation in case of brittle materials. Okay. So next is the
Yes,
concept
Ron.
of factor of safety. So in design of measurements, or this is a practical subject, right? So practical subject in the sense you will be designing the components and parts of automobiles or even other machine components, etc. So will be used in real practice. So there you need to assume this factor of safety. What is factor of safety? Is it's just a ratio of quantities. It is a unitless or a dimensionless quantity. It is just ratio of this similar things. So let's say strength, which is also is represented in Newton per mm square or Newton per meter square. Stress also is the same thing, Newton per meter square. So usually you will have factor of safeties which are given. So this is deterministic. Okay. So in the sense, suppose you take an aircraft. So in aircraft, the factor of safety is very small, like 1 to let's say 1.5. This is for aircraft and stuff. Aircraft. So this is the factor of safety over there. Whereas if you see in satellites and stuff, uh, satellites or spacecrafts, the factor of safety will be like less than 1. And even in cases of like take for example lathe beds and stuff, no. So there the factor of safety will be like 5 to 8 or something around this size. Even in gears, heavy duty gears and stuff, the factor of safety will be around 3 to 5. So can you see a pattern here? Okay. Do you see a pattern like as and when you decrease the factor of safety, what happens is the weight mass which we are talking about, the density of material which you are using, or directly related to the mass of the components, is reducing. Okay, so that is indirectly what is factor of safety. So whenever someone talks about factor of safety, you can directly relate that to the mass and several other properties which are related to mass overall, right? And also sometimes related to strength. So failure criteria, if you see, it is more for satellites and aircraft rather than lathe beds and gears. Okay, so the amount of forces is nonetheless almost similar to their own criteria, but what happens is lesser the factor of safety, more lesser will be the weight. Okay, lesser will be the weight, and of course, obviously, we need lesser weight in case of satellites and aircrafts here. Whereas in case of lathe beds or even any machine tool beds, gears, there is no need to reduce the weight and stuff. So we need more robustness over there. At the same time, we can't have robustness in aircrafts and satellites, or else we'll compromise on the efficiency. So this is a trade-off. So that's the factor of safety. Nonetheless, factor of safety will be considered for all the components which we'll be designing, right? So I'll give you the detailed set of procedures when we start solving the numerical. The factor of safety is different for the different materials, failure criteria of materials. So it is usually depicted as FS or FOS, factor of safety. Let's say here the FOS, or it's sometimes denoted as a small n. So N or FOS are F subscript S. So some textbooks refer to this, and some textbooks are referring to this thing here. So we'll use the same notation throughout the course. Factor of safety, failure stress over allowable stress, or failure load over allowable. So you see here it's unitless. So it's here load is newtons by newton. So here also it is Newton per meter square, or again here also it is Newton per meter square. So the units they cancel out. So that's why this factor of safety is dimensionless, right? And again, this varies. Okay, how you calculate the factor. Suppose you know the stress, how much stress is being acted. Okay, so suppose you have a bar being pulled on both the directions. You know the load being applied here. So if you know the load and you also know the, let's say this is a cylindrical one and you have a circular cross section. Okay, you know the area also. So thereby you know the stress. Once you know the stress, you will be asked sometimes to calculate the factor of safety, or you will be asked to calculate the yield stress, right? So you need to trade off here. So let's say you use if this is for a ductile material. So how do you choose whether it's ductile or you want a brittle material? Again, if you want some warning, okay, you need a warning before it is failed, before it completely fails and stuff. So you need a warning, or let's say you need it to be used for both tension and compression. Tension and compression. So you need to be used for both the cases, that is tension and compression, and you need a suitable warning before it fails, right? So in those cases, you will go for the yield stress. So that's how you identify. The SYT is nothing but sigma YT. So don't get confused. So sometimes this gets mismatched. So most of the time I'll be using sigma. So this is, I think I took it from the Bandari textbook. That's why it's looking like this thing. So sigma YT is the yield stress, and you'll have a certain degree of warning before it fails under the applied load here, right? So in that case, you use ductile material, and, or you assume the factor of safety depending on what type of component it is, and we have a data handbook where you'll get to know what is the factor of safety of each components which are used in different conditions, and then you can find the particular material. Sigma YT is nothing but you'll get this to the material part, or whatever material you need, you can extract from this data. Similarly, it goes for brittle material. So brittle material, whenever use it for only compression. Okay, most of the times brittle material they are good in compression and not that good in tensile. So most of the time brittle material are used in compression. Okay, so thereby in that case we'll use this ultimate stress. Okay, sigma utility. So ultimate stress of the material is required, and we'll assume that particular material from the data. That's how the flow is. For fatigue failure, I think sir has already started the other session. So you have fatigue failure, you have endurance limit. So it's no longer denoted by sigma y and sigma u. It is based on this, but not entirely on this thing. We just assume the endurance limit stress on this. That will be sigma minus 1 something. That's an endurance. So what all this factor of safety depends on? If you ask, so it depends on effect of failure. So what is the severity? Okay, like you want some warning or not, like that. Type of loading also varies. Whether it is static or it is fluctuating or time based. Okay, it is going tension, compression, and oscillating between these values. Those kind of stresses, or it is just either tensile or compressive, like that. And degree of accuracy in force analysis, or whether it is high for low accuracy, means whenever there is a accuracy of whether the stresses are being applied exactly at the centroid, or any other things. So those kind of accuracy, that in the sense. So let me give you an example. So you have let's say some component which you are compressing. Okay, you have the central axis of this here, and suppose you are acting the force over here. There's offset, right? So there is some amount of eccentricity here between the forces applied and the centroid. So in these cases, it is neither tension nor compression. So over this area, you'll have compression, and here you'll have tension. This will go up and this part will go down. Right. So that's what you mean by force analysis. Okay, degree of accuracy, whether it's exactly at centroid or not. All those things you need to be taken care. Then material of the component, whether brittle higher, the more brittle, the the higher will be its load carrying capacity, but at the same time it will be brittle. It will break off. Then reliability, cost, testing. Even for testing, you need to have this standard testing conditions and all those things. Right? And service condition, how well it is, how frequently it is oiled, or so lathe beds in the sense, lathe beds or machine beds in this sense, they can have higher factor of safety because of this. They can be cleaned or on those things. In case of aircraft, you can't perform those that frequently. In quality of manufacture also matters. So whether higher or low quality, higher the quality, you can decide on lower the factor of safety. So these are the things which factor of safety depends on. Impact we'll discuss in some other class. So we'll start off with the basic types of stresses. So this is type of stress. You're very familiar with this. The tension kind of test or tension kind of a stress. Similarly, strain. We're talking about stresses, right? So when we start off with types of stress or stresses, I told you before that there is a tensile, or you can say normal stresses. Normal stresses. Here again, it splits as tensile and compressive. Splits as compressive. Right. And we have a second type, that is shear, or you can call it tangential. Third one is bending. Fourth one is you can say bearing. Bearing. Fifth one you can call it as torsion or twisting. Twisting stress. So these stresses I think you're already familiar with. The tensile is the one where you have longitudinal stress being applied, and compressive longitudinal stress but in the opposite direction. So we've all discussed before. Let's move on to the next kinds of stresses. So this I discussed in the PPT. Let's call next topic uniaxial. Uniaxial stress. So uniaxial, the name itself suggests it is uniaxial, so single axis stress. So the stress acting on plane along only one coordinate axis, then it is referred to as uniaxial stress. So let's say suppose you have a 2D plane here. So you have a 2D plane, and stresses are being acted on this direction, or forces are applied in this direction. So we have stresses which will go along this. So sigma x. So let's say stresses will be act in unidirectional state here. Okay. Now, in this stress system, you don't know how the component will break, and you want to find some stresses which are acting at any inclined plane here. Suppose there is an inclined plane, let's say over here, okay, at an angle of theta. So at an angle theta, normal to this, let's say you want to find what is the stress acting here. Okay, you can call this sigma n or normal stress. So what is the stress acting here? You want to know, just to assume. Okay. So normal stress in an arbitrary plane. Normal stress on an arbitrary plane that is inclined at an angle of theta. See, inclined at theta. So this, you can directly write this as sigma theta equal to sigma x cos square theta. You can write it directly by geometry, directly come to know. So this part is a square. So this is given in equation 2.13. What is this 2.13? So I'll share with you a handbook. Let me show it to you. Okay, so this is the handbook, design data handbook. I'll just share it with you in the group and check it out. Here you can find equations, whatever I uh, 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 derive. So the equations will be available here. So let's say here, figure 2.4, whatever I've drawn is available, I think, over there. So 2.4, check it out. So this is the equation. This is the two-dimensional plane where you are applying the forces over here and here, and you want to find the stresses at an angle of theta. So this is the normal line which is going to sigma theta. Okay, so for this sigma theta, what is the stress here is this value, what I have written here, sigma x cos square theta is given in equation 213. Okay, so that's the thing I've written here, 213. Similarly, shear stress also acts along with it. So if this plane, if you magnify, right, so how does it look like is like you have a normal plane. So along this plane you have one stress, that is sigma theta, and another stress will be acting around exactly like shear, exactly perpendicular to that, and that will be tau theta. Okay, that's the shear stress acting on that plane. So even though you're applying only tensile load, but if you take a plane inclined at some angle, so for that you will have a normal stress acting at that plane and also shear stress. So ultimately it will break, right? So once it breaks, that means you have a shear stress. So that's the normal stress. Let's say shear stress. Shear stress acting on that plane will be given by tau theta, that is equal to sigma x by 2 and sine 2 theta. Okay, this is given again equation 2.14, the data handbook. So this forms the basic equations for us to solve a two-dimensional problem. Similarly, we'll evolve further this 2D problem, and how this can be integrated into our numerical problems and further simplification, right? So this was about uniaxial stress. Now let's go on to the biaxial stress. Let's say biaxial stress. So in biaxial stress, you can just identify the same rectangle. So here the stress was applied in one direction, right? In the previous one, now I'll apply the same stress in two directions. This is sigma x and this will be sigma y. So this is biaxial and it's a tensile kind of a stress. So again here I want to find what are the stresses or combination of stresses which are acting at this particular plane here. So I'll just write here this thing as theta. Okay, so at this inclined plane I want to find what is the stress, what is the stress acting here. So normal to this, I'll just take a straight line. This is my normal stress or stress inclined at that angle theta. Okay, so if you analyze this, you can close this figure. So let's say I draw a dotted line over here. Okay, and I close this somehow. Okay, where this line will represent force F1. F1 is nothing but force which is acting on the x direction. F1 force is nothing but sigma x times this BC. Oh, I didn't write the notations, right? So here, let me call this A, B, C, and D. So that's the 2D planar figure. Okay, so stress. What is stress here? Stress is nothing but force times area, right? Okay, how I got this F1 equals sigma x b. That's how I'm stating here. So I told you along the x direction you have sigma x, that is stress. Force I'm just denoting as F1 over area. If you check now, this is the area in which it is acting, BC. BC is the cross sectional area where it is acting, so I can write it as BC. So thereby, whenever I want to find the force, so this is triangular law of forces. So this force here can be represented as F1 equal to sigma x times BC. So that is what I've written here. Okay. So similarly, this component here, this component can be written as sorry, I just wrote it in a different manner. So that is actually this stress acting at this particular area. Okay. So I told you I was right about this force being acted, but the direction is here. So if you close this triangular law using the triangular law of forces, so this here, this line will represent F1, the force. Okay, so we have drawn the triangle right over there. That's sigma x BC. Okay, similarly, this line, since theta is here, there is nothing but is equal to theta here. You can translate that theta over here, and this will be F1 Okay, sine theta. Okay, this length here. Similarly, this length can be represented as f1 cos theta. Okay, this will be cos component, this will be a sine component. You have your perpendicular here, and this will be represented as sigma x b, right? Similarly, you can do the same thing over here. Fy, you can consider this line as f2. Suppose if I draw a straight line over here, okay, so this can be written as f2. Force f2 is equal to sigma y times this dimension here. Oh, I didn't name this yet, so let me name this E. So it's just this area I can consider. So EC. Okay, F2 is sigma y. Now you got the flow, right? Now, so this stress system, which in which direct stresses are acting, that is two mutually perpendicular direction along x-axis and y-axis. So such type of stress is called a biaxial stress. In this condition, how you define is, let me consider the total forces. Total forces perpendicular in perpendicular to the plane. So if you find the total forces, no, so you'll get Fn or Fn or F theta. So this is nothing but forces acting along the normal direction of the plane. I'll just draw it. So you have the normal, right? So here is sigma n. So what is the force acting here? You want to show, as we can write as Fn equal to F1 cos theta plus F2 sine theta. That is that's how you can represent the summation of two forces. That is resolving these two forces. Okay. Also you have Fn, the normal force, is equal to sigma theta. This is sigma theta or n or theta. You call it both. Right? So F theta to Be. Be is the area again. So force equals stress times the area. So Be is the area here. You can see in the figure. So continuing further, now let's combine these two equations. Fn RHS and LHS. Let's write it like this. So sigma theta into Be equals sigma y. So this F1 I'm writing in terms of stress now. Fy EC then cos theta plus again F2 I'm writing in terms of the stresses. That is you have sigma x EC. Oh, sorry. This is BE EC EC and this is EC sine theta. So condensing this further, you have sigma theta equals sigma y into BC by BE cos theta plus again sigma x into EC by BE into sine theta. Now check out what is BC by BE and EC by BE. So BC by BE, okay, is nothing but opposite over hypotenuse, right? BC by BE. BC opposite over the hypotenuse. You have theta here. You can see this particular triangle I'm talking about. Similarly, EC by BE. EC by BE is sine theta. Okay, is adjacent opposite by hypotenuse. This is adjacent by hypotenuse. The previous one is opposite by hypotenuse. So that's how you get sigma theta here. Sigma theta is sigma y. This here becomes cos theta. So therefore, this can be written as cos square theta plus sigma x. So EC by BE, this can be written as sine square theta. Right. So further simplifying this equation, sigma theta. So how can you write cos square theta? You can write, let's start with sine square. Let's flip this over. So sigma x sine square theta can also be written as 1 plus cos 2 theta by 2. Right. So similarly, sigma y. Sigma y can be written as sigma y as it is cos square can be written as 1 minus cos 2 theta by 2. Okay. Now check out what is common. Next point. Okay, only that minus sign is common. If you multiply this, you will get sigma x cos square 2 theta by 2, and sigma y cos square 2 theta by 2. So we have cos 2 theta is common. So once you take out that commonality, so what you get is sigma x plus sigma y by 2. So once you multiply this inside of the sigma x and sigma y, you get this plus, and here you can get sigma x minus sigma y by 2 into cos 2 theta will be common for both. And check it out here. So this equation is given in the dead end. Equation 2.28. So I'll show that equation to you. Right here. So you can see here, equation 2.28, you have normal stresses. That is, if you want to find in a biaxial stress state, you want to find the stress at any angle, any inclination inside the plane, then you can use this formula to extract that information. That particular stress, normal stress, which is acting over there, you can just find that. That's the advantage. And this forms the basis for our next very important derivation, that is principal stresses, right? Biaxial with shear, and next for principal stresses is very important with the subject point of view, right? So similarly, you can find what is the shear stress. You can see the very next equation. So this equation you can directly plug it here. That is shear stress acting, shear stress tau theta. So shear stress, you know where it is acting. So if I were to draw over here, it will be acting like this. Tau theta. Shear stress acting tangentially to the plane. So tau theta is equal to sigma x minus sigma y by 2 into sine 2 theta. So this is again in equation 2.29. Suppose you want to find what is the shear stress acting on that particular portion, so then you use this to find the shear stress. Now let's come to the last case. The last case is biaxial stress system with shear. This is including shear component, one shear component here. So last problem which we did, it was just biaxial, where stress were applied in sigma x, sigma y. Now we are doing this along with the shear component. Let me so let me name this A, B, C, and D. And this component here now is subjected to sigma x, then you have sigma y, then sigma y. So whatever cases I'm writing here is all positive. Okay, positive. And one more shear. This here, tau x, y. And also on this line here, and in this line. So this is tau y x. So these are shear components which I have just added over here. So along with the usual sigma x, sigma y stress components, you also have, in addition to that, a shear component. Now again here, let's say I want to find what is the stress acting on this plane. Okay, there is I'll take this small angle theta here. So I want to find the stresses here. Again, I'll denote this as sigma n or sigma theta for simplicity, sigma theta, and also shear stress, shear components. Tau theta. Okay, so now I need to consider along with the previous ones, that is the shear stress also. Okay, so this is where there is another derivation which is continuing with this. So I won't do that derivation. I'll just simply straight out write the equation. So this stress system is where shear stress also acting on the plane. You can see there are along the plane ABCD, we have shear stress components also added along with the mutual perpendicular planes. So this forms the basis for all our numerical problems which are subjected to multiple stresses and stuff. So whenever a component is subjected to multiple stresses, this is the worst case which we can assume. You have stresses, also you have shears in all the directions. Okay, so in this case, what is the normal stress? Normal stress on inclined plane. Normal stress on the inclined plane here is written as sigma theta. You can see there is a small connection. The first two equations are the same. So sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus along with. So still here it is same as that of the previous one. Now there are shear components. You add that shear component tau xy sine 2 theta. You just add another shear component. That's it. This is also given. This is given in equation 2.32. So similarly, we ask about shear stress. This tau theta. Also, there is only small change here. So, but here it is negative. Negative sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. So that is equation 2.3. So these are the equations. These are the two equations for which act as a base for our next equation which is coming. So I'll just give you those two equations directly. But before that, a little bit of theory. So any doubts so far, you can let me know in the group chat. These are all you are familiar with. Right here. This is the one. So in four-dimensional stress system, no, so when a component subjected to different types of stress. Okay, for example, as transmission shaft. You check it out if in a transmission shaft, what all the different types of stresses are being added. Okay, transmission shaft here. Okay, let me just draw a shaft here. So this shaft, let's say, is just fixed at one point, or simply it is supported. It will be rotating, right? It will be twisting, be rotating rapidly. Also, sometimes it will be subjected to loads here and there. Okay, you will engage gears, right? So gears will be engaged over the course of this shaft. So therefore, you will have loads also, and you will be twisting also in this shaft. So in this case, whenever you are applying multiple loads, you cannot analyze this in piece by piece method. So that is where principal stresses come into picture. Okay, so principal stresses are the stresses, as the name itself is indicating. It is a principal. This is the main kind of stress which is we need to find, or depending on that, you need to design the component. So that's called as a principal stress. So we'll not go much into the derivation of that. Okay, just we'll say we'll write the equations. I'll just show you the equations just here. Yeah, see these two equations here. See these two equations here. Okay, maximum principal stress and minimum principal stress. So the derivation will not go into this much. So it is derived from the previous equations, whatever we have defined so far. So these two equations will be used in most of the formulae to find the values, or find the stresses, depending on which we will find further the values of the principal stresses. So we'll solve some numericals on this probably in the